Okay, so already we discussed about the Dirac-delta function, and we discussed the Gaussian integral, which are the two very important tool for the foundation of quantum mechanics. As I already mentioned, our this course, or these lectures, or these videos are for the to build up the foundation of quantum mechanics. Okay, so today I want to discuss another important tool for the quantum mechanics, that is Fourier transform. And I will try to explain Fourier transform from Dirac delta function, because we already discussed a part of the few important part of Dirac delta function. So I will try to explain. I will try to explain the Fourier transform with the help of Dirac delta function. So that will be help you to connect whatever we discussed till now. Okay, great. So let me share the screen. Great. So let me remind you what we discussed till now in Dirac delta function and the concept which I am going to use today. So okay. So what we defined already. So in one of the previous video about the different representation of Dirac delta function, I already discussed the integral representation of Dirac delta function, delta of x minus x prime. And if you remember, we define, like, I will give the video in the description, 2 pi from minus infinity to plus infinity e to the power e to the power I k x minus x prime dk. Okay, so this is already what we discussed about Dirac delta function. So if you remember what was Dirac delta function we defined Dirac delta function delta of x minus x prime. We said this is infinity at x equals to x prime, and it is 0 at x not equals to x prime. Okay, and so also if I also discuss this part which I'm going to use today. Let me define one more important mathematical integral formula or integration, e to the power minus alpha x square plus beta x dx. So do you remember what was the integral value we calculated? Exactly, it was pi over alpha e to the power beta square over 4 alpha. So this is very important tool for us in different part of quantum mechanics. Great. And now let me just remind one more thing what we discussed. We we discussed one important thing, like, let's consider a function f of x. So what is f of x? F of x is a well-defined function. Okay, let me just note down. It is a well-defined function. Okay. Now, if one, let me draw this one. So whatever we discussed, let me show you in a graphical way. Perfect. And let go from down. X. Let consider the not. I don't need. Well, let consider this is x prime. Okay. So according to the definition of Dirac delta function, If I want to show you the graphical representation of this Dirac delta function, so this will be, so at this point at x equals to x prime, it should be got some spike here, and this spike in such a way that the area under this curve, that is 1. Okay, now, and also if we define the function f of x at the same plot, okay, then so this green is, the blue one is f of x, which is a well defined function, and the green one is our delta function. Okay. So do you remember how we, so what is this integral value we discussed already? Where is my block? My favorite. Okay, so what is the integral? Do you remember this one? F of x delta of x minus x prime dx. So this should be f of x prime. Why? Because in this range, when x is not equal to x prime, your delta function is 0. So there is no contribution of the integral from minus infinity up to x prime, and also there is no contribution of this integral from x prime to plus infinity. So we got only contribution in this range, and at x equals to x prime, when the delta function is infinity, so at this point the function f of x is nothing but a constant. That will be the constant means the function at that point. Okay, great. Now suppose if I told you, so, okay, that can you calculate this, can you define the function f of x in terms of delta function? Is it possible? Can you do it? Yes, right. So this should be, we can, so it is very easy. Let take me different color. Let, what will be happen if I take the prime here and if I take the prime here? So that I change the variable. So this should be f of x, right? So one can write the function, any function, in terms of delta function also. From minus infinity to plus infinity, f of x prime delta of x minus x prime dx prime. Okay, great. Now, if we remember the integral representation of delta function, which I discussed in one of the previous discussion, where I discussed defined representation of delta function. If you want, you can see in the description. There is a I put the link of this particular discussion. So this will be 1 over 2 pi from minus infinity to plus infinity e to the power I k x minus x prime dk. Okay, so this is what, that's why what we discussed step by step. Okay, great. Now let me write f of x. So now we will get two integral. So one integral on x prime, where is already there, and another integral we get for delta function. Okay, and both in the same limit from minus infinity to plus infinity. So this will be, let's take 1 over 2 pi out. So there is two integral minus infinity to plus infinity. There is one more integral minus infinity to plus infinity. So, and there will be one function f of x prime. In a for delta function, you will get I k x minus x prime. Okay. So for this delta function, you will get one dk, and there is dx prime. Okay. So you can just compare. So so whatever this delta function, we inject this at this point. Okay. So now let me write in not little bit different way. I take one of the integral from minus infinity to plus infinity, 1 over square root of 2 pi from minus infinity to plus infinity, f of x prime e to the power minus I k x prime dx prime, and there is one term, it is plus, this plus term is there, I k x. Can I write it like this? Nothing, I just rearrange the terms. Okay, right? Now, whatever with this term, so this term, so we can write this term as a f of k, because we integrate over k, integrate over x, so this is function of k. Okay, where so f of k that equals to 1 over square root of 2 pi from minus infinity to plus infinity, f of x prime e to the power minus I k x prime dx prime. Okay, so we can write whatever our f of x, that will be in terms of f of k, it will be 1 over 2 pi from minus infinity to plus infinity, f of k, and if we just go up a little bit, it will be plus e to the power I kx d k, it will be function of x. Okay, and these two are very well known Fourier integral theorem. So these are known as Fourier theorem. So if someone give you some function in which is a function of x or in the position space, you can convert this function which is in the position space to k space, and also you can use the inversion. So this is a very important very important concept to build up the foundation of quantum mechanics. So we use this concept many times in quantum mechanics. So this is a thing you have to understand, and this is very easy to understand. Why are you doing like this? Because we had already discussed Dirac-delta function. So that's why I was thinking to how I can interconnect between the Dirac-delta function and Fourier transform or Fourier integral. So nothing you have to remember. Everything is going step by step. Great. Now let's take one example. It's clear till now, right? Great. So let's take one function f of x equals to a e to the power minus x square over 2 sigma square. Okay, so this is a function of x. Now if someone want to draw this function, how this function will look like? So we know this is a Gaussian function at x mean at x equals to 0. Okay, this is function f of x, draw here. And so this function will be something, let me take different color. If we draw this function, something like this, where a is the normalized constant, and this will be your sigma, right? With our distribution will be sigma, and here mu equals to 0, and this is your a normalized constant. Am I right? Great. Now, what will be happen if someone want to transform this distribution from f of x to f of k, or let me, can we calculate this one? Yes. What we have to do? We have to do Fourier transform. Let's try to first do mathematically. Then we'll try to show you and explain you using Mathematica, which is one of the software and which is very useful for us. So if we want to calculate f of k, so this will be 1 over square root of 2 pi from minus infinity to plus infinity f of x e to the power I kx dx, right? So it will be a over square root of 2 pi from minus infinity to plus infinity e to the power minus, what is the function you consider, x square over 2 sigma square e to the power I kx dx, or we can write this like a over square root of 2 pi from minus infinity to plus infinity e to the power minus x square over 2 sigma square plus I kx dx. So do you remember we did in the very beginning? I just remind you what we discussed in one of the integral, like from minus infinity to plus infinity e to the power minus alpha x square plus beta x dx, that is square root of pi over alpha to the power beta square over 4 alpha. Okay, so if I compare between these two, so our alpha, that will be 1 over 2 sigma square, or 1 over alpha, which is going to use 2 sigma square, and beta, that will be pi k. Just compare this with this. Okay, so what we got, a over 2 sigma 2 pi, sorry, and so it will be square root of pi by alpha, so it will be pi into 2 sigma square. Okay, and then no, it is not x. Okay, this is not x, this is dot, and then it will be e to the power b square. B is I k, so b square will be, so from here we can want to use b square minus k square, so minus k square, and 4, take 4 here, and 1 by alpha 2 sigma square. So it will be a into sigma e to the power minus k square by 2 sigma square. So whenever we do the Fourier transform of any Gaussian function, it will be remain Gaussian. But what will change here? Let me just once again draw for you x. In this one, I want to draw f of x. At the same time, k. I want to draw f of k. Okay. So what is the function? It was a e to the power minus x square over 2 sigma square. So when you draw this function here, this was something like, so this was your a. I already discussed this part. So what are the height of this distribution will be a, and width of the distribution, this was sigma. Now the same thing, f of k, what will happen here? Now see, your normalization constant is multiplied with sigma. So this will be decrease. And width of the function will be, instead of sigma, it will be 1 over sigma. So this will be something like, so this will be your, depend on the value of sigma, and this will be your 1 over sigma. Okay. So now let me give you input of quantum mechanics a little bit. Okay. Let's consider a particle, and the dynamics of this particle is represented in the position space, suppose f of x. Okay. And whatever, and the function is that consider localized within a distance delta x, and that should be of the order of sigma. Okay. Now what will happen if we want to see the dynamics of this particle in the momentum space? So that will be defined using, the dynamics will be defined using f of k, and the function will be localized in k space, that should be of the order of 1 over sigma, what I just will discuss. Now, so this is a very important thing what we're going to discuss. So let's consider the particle is localized within position x, which is delta x, and in momentums in k space delta k, that will be of the order of sigma into 1 over sigma, that will be sigma times 1 over sigma, so of the order of 1. And this is the input of quantum mechanics, which we define as Heisenberg uncertainty principle, which we're going to discuss in next one of the video about quantum mechanics. So this is the foundation of quantum mechanics. So what we did, we start from delta function. Okay, from delta function, we define or we discuss Fourier, right, integral. From that, we give you the input of quantum mechanics, which is Heisenberg principle, which we discuss in details in next lecture. Now, let me give you one short uh, important information or important thing. The same thing what we discussed just using Mathematica. So let me define a function f of x, okay, which is a e to the power x square over 2 sigma square. I define the function. Now let me plot the function. And I plot the function. So here I consider a is 0.5 and sigma is 0.8. And I plot the function from minus 0.5 to plus 0.5. And you can see the height of the function is 0.5 and width is 0.8. Now let me calculate the Fourier transform of this function. So in Mathematica, there is already defined package for Fourier transform you can use. And if we do the Fourier transform of this function, you can see it is a 1 over sigma square. So it will be a sigma e to the power minus half k square sigma square. What we discuss here, let me check. So we get a sigma e to the power k square by 2 sigma square. So we get the exactly same value of the Fourier transform. Okay. Now let me plot these two together. Okay. Now you can see. So in this function, red one is your the function in x, blue one is function in k. So here height is decreased, but width is increased. And the product of the width for this x and k, it should be of the order of 1. So this is a very interesting. So I use this Mathematica sometime to show you some graphical representation whenever I need something to discuss and something to show. So our main motivation was to discuss from Dirac-delta function, to Fourier integral. I hope you understood, and it is very easy to understand this part, but it's very important even to understand. So in the next discussion, we will try to explain once again, and then we will start step by step the foundation of quantum mechanics. See you till then.